Hi everyone. Today let's talk about work and power. And we first start this discussion by talking about its definition. In physics, work is defined as something done by a force on an object when the object is displaced in the direction of the force. So in mathematical terms, the formula is translated to W is equal to Fd, where W is the work done, F is the force acting on the object, and D is the displacement. So its SI unit is in joules, which is also equivalent to Newton meter. In here, the force corresponds to Newton, while the displacement corresponds to meter. Work is a scalar value. So that means it can be positive, negative, or zero. So when does it become positive, negative, or zero? Let's talk about that in our table here. We examine the relationship between force and displacement. If they are moving in the same direction, then they are parallel to one another. The work done here would be positive. But if they are moving in opposite directions, they're still parallel to one another, but the work done is negative. But if they are perpendicular to each other, of course, the relationship would also be perpendicular and there would be no work done. Let's apply that to a conceptual exercise right here. We have a couple of situations, the first one being a box lifted off the ground. The object here would be our box. The force is applied force. The direction of the force is upwards. And that's also the case for the direction of displacement. In here, the work done is positive. But what if we have a box carried and moved horizontally? The direction of the force would still be upwards. The direction of the displacement is sideways, so to the left or to the right. But there would be no work. If a ball was launched horizontally, we have applied force to a ball, and the direction would be to the left or to the right, horizontally. That's also the case for the direction of the displacement. In here, we have positive work done. Okay, say we have a ball on a spring being spun around a circle. So the force applied here is tension to a ball, and the direction is towards the center or the other end of the string. The displacement direction is to the left or to the right, perpendicular to the string, but there is no work done. In our last situation here, we have three sub-situations. We have a man supporting the slow but constant descent of a box on an inclined plane. So this is an example of an inclined plane. Let's say the box is right here in the middle. If the force acting on the box is gravity, then the direction of the force would be downward, and the direction of the displacement would be parallel to the incline downwards, and there would be positive work. However, if there's an applied force by the man, then the direction would be parallel to the incline upwards, and the displacement direction would also be parallel to the incline but downward. So there would be negative work. And say we have friction applied to the box, then the force direction would still be parallel to the incline upwards, and the displacement direction is still also parallel to the incline downwards. So that's also negative work. All right? Applying what we know and the formula that we have, let's try solving this problem here. A 0.14 kilogram ball is thrown straight up into the air. The hand exerts a constant force of 2 newtons over a distance of 1.2 meters. So what does that mean? A ball of mass 0.14 kilograms was thrown up to a maximum height of 1.2 meters with a force of 2 newtons. So we're given M, or mass. We're also given the displacement D as 1.2 meters and the force F as 2 newtons. Let's try drawing a free body diagram here. Let's say this is the person holding the ball. Let's put that in an axis here. And let's say this is 1.2 meters. All right. So as the ball is thrown up and it reaches the maximum height, as it falls down, gravity is acting on it. But the force initially applied was 2 newtons. So after drawing this diagram, we know that we have applied force upwards and the direction of the displacement is also upward. So same direction as the force. Is there work? The answer is yes. With the magnitude of the force being 2 newtons and the displacement being 1.2 meters, the force and the displacement point in the same direction and the work done is expected to be positive. The magnitude of the work done can be calculated using this formula. W is equal to Fd. So we simply multiply 2 newtons to 1.2 meters and we get 2.4 joules. For part B, we're talking about the descent now. So the force here would be gravity downwards. And the direction of the displacement is downwards as well. So still same direction as the force. And in here, Fg stands for Fgrav. And the force of the gravity should be equal to mass multiplied by g, where g is the acceleration due to gravity. So we know that that's just 9.8 meter over second squared. We multiply that and we get 1.37 newtons or 1.4 newtons. So its direction is naturally downwards. The displacement from the maximum height to the thrower should be the same. D is equal to 1.2 meters and should also point downwards. And as expected, the work done here is positive. In here, the magnitude of the work done by gravity is W is equal to Fd. We already got F, so we just multiply 1.37 newtons to 1.2 meters here, and we get 1.64 joules. All right. Now let's move on to the second problem, work done by friction. In here, we're asked, how much work did the friction do horizontally when movers pushed a 46-kilogram crate 10.3 meters across a rough floor without acceleration if the effective coefficient of friction was 0.50? So again, we're given the mass. That's 46 kilograms. The displacement is equal to 10.3 meters. And the coefficient of friction is 0.5. So let's draw a diagram here. Let's say this is the person and the person is pushing this crate. Let's say this is our axis here. This is 46 kilograms. And again, the coefficient of friction is 0.5. So the force is applied force to the left or to the right. The direction of the displacement is also either to the left or to the right. It's in the same direction as the force. And is there work? The answer is yes. All right. Now let's draw in the diagram the forces. So in the crate, there is F grav acting on it. That means there is also normal force. And again, we have applied force. We also have friction in the opposite direction. So again, the displacement here should be in the same direction as the applied force. And in here, in this problem, the magnitude of the frictional force is given by F fric is equal to nu multiplied to n, where nu is the coefficient of friction and n is the normal force. So in our problem, the normal force is equal to the gravitational force, and that's given by F, n is equal to mg, where m is the object's mass and g is the acceleration due to gravity. And since we're only dealing with magnitudes, signs can be addressed later. Right? So plugging that in here, we have nu mg, and plugging in the values that we got, we multiply 0.5 to 46 kilograms and to 9.8 meter per second squared. And you finally get 225.4 newtons. So we use this value to solve for work. We get work due to friction is equal to FD. So we multiply 225.4 newtons times 10.3 meters. And we get 2321.62 joules. But where is this negative sign coming from? It's because the work done by friction is anti-parallel to the direction of the displacement. Since that's the case, it implies that it is negative work done. All right. Now let's move on to the third problem, finding force from work. Let's say we have a baseball player doing 1,400 joules of work when hitting a baseball into the left field. So assuming that the baseball landed 60 meters away from the home plate, how much force did the player use to hit the ball? Let's try drawing a diagram here. Let's say this is the baseball player. And he's holding a bat right here. Let's say this is the ball. And we're given a displacement of 60 meters. Again, the work done here is given as 1,400 joules, and we're being asked for the force. All right? Let's write down that values here. And the force is applied force to the left. The direction of the displacement is also to the left. So same direction as the force. Is there work? The answer is yes. And in this problem, the applied force is as instead of work. From the formula, W is equal to FD. So we divide both sides by D. which is why we have the formula F is equal to W over D. Plugging in the values that we have, we divide 1,400 joules by 60 meters, and we get the magnitude of the force as 23.3 newtons. So that's our final answer for this problem. All right, now let's talk about power. How does power differentiate from work? In physics, power is defined as the work done in a given period of time. It is obtained by dividing the work done during a time interval by the duration of the time interval. The power obtained this way is specifically called the average power, and the SI unit of power is watt, which is also equivalent to joules per second. So it's a fraction because, again, power is the rate at which work is done. And in here, we also have a formula for constant velocity. And that implies that force and velocity are moving in the same direction. This first formula is useful if the work done is already given. So this is a bit trickier because we need to determine first the components of force and velocity that face the same direction, which is similar to how we obtained work. But just like work, power is a scalar quantity. It can be positive, negative, or zero depending on the magnitude of work. So if the work done is positive, then the power is also positive. And if the work done is negative, then the power is also negative. If no work is done, then no power is also applied. Let's try solving this first problem here. A 50-kilogram marathon runner runs up the stairs to the top of a 500-meter tall building. To lift herself to the top in 20 minutes, what must be her average power output? So let's draw that diagram here. Let's say this is the building and it stands 500 meters. These are the stairs. And let's say this is the person running. So of course, we have force acting on the person, but there's also upwards motion to reach the top. So the time given here is 20 minutes. And again, the mass is 50 kilograms. This will be our displacement. So given the quantities, even though the work is not a given, we can easily solve this using the force of gravity, which is the force acting on the person, and the displacement. So again, we just multiply the acceleration due to gravity by the displacement or the height. So we get this formula here. Work is equal to mgh or mgd. We multiply 50 kilograms to 9.8 meter per second squared and also multiply 500 meters before finally getting 245,000 joules or 2.45 times 10 to the 5 joules. Okay. Using this, we can now solve for power exerted by the runner. Using the time, we divide this work by 20 minutes, but first we convert that to seconds. Using dimensional analysis, we get 245,000 joules is divided by 1,200 seconds before finally getting the quantity 204.2 watts. So that's the average power output for this problem. All right. Now this problem asks us, should you walk or run? It is 5 kilometers from your home to the physics lab. And as part of your physical fitness program, you could run that distance at 10 kilometers per hour, which uses up energy at the rate of 700 watts. Or you could walk it leisurely at 3 kilometers per hour, which uses energy at 290 watts. Which choice would burn up more energy? And how much energy in joules would it burn? Why does the more intense exercise burn up less energy than the less intense exercise? So again, let's try drawing that diagram first here. Let's say this is your home. This is you. And this is the physics lab. The distance here is given by 5 kilometers. And let's use different colors for each scenario. Let's say you're running at 10 kilometers per hour. That's 700 watts. But if you're leisurely walking, that's 3 kilometers per hour, and that's 290 watts. Okay, given the displacement, velocity, and power, we just plug that in. T1 would be D over V1, which in this case would be 5 kilometers over 10 kilometers per hour. So that's 0.5 hours, or if converted, we have 18,000 seconds. So T2, on the other hand, would be 5 kilometers over 3 kilometers per hour. That's 1.67 hours. So that's equivalent to 6,000 seconds. But since P is equal to W over T, we can also compute for work done using W is equal to PT. So we plug that in right here. For the running, we multiply 700 watts to 1800 seconds. We get 1.26 times 10 to the 6 joules. For walking, we multiply 290 watts to 6,000 seconds. We get 1.74 times 10 to the 6 joules. And the conclusion is that walking actually uses more energy. Thus, the second case, which is walking slowly using less power, would have more work done and burn up more energy than the first case. So it's up to you which decision you would make here. But at least these values provided you insight on which burns up more energy. So this is the last problem here. You'll be giving a supplementary document for you, and we will leave this last problem for you as an exercise. Again, thank you for listening, and I hope this has helped you understand work and power more.